Have you ever wondered how far inward the universe can be explored? Not outward toward distant stars, but inward into the smallest depths of reality. Is there a final point where curiosity must stop, a quiet boundary, where the universe no longer allows us to look closer? And if such a limit exists, what does it tell us about the nature of the cosmos itself? As we drift gently into that question, we discover something remarkable. Two different lines of reasoning, one from gravity, one from quantum theory, lead to the same boundary, the Planck scale. Here we reach a sharp boundary at roughly 1.616 times 10 to the power of minus 35 meters, known as the Planck length. At this scale, the physical laws we use to describe the universe no longer agree with one another. As we zoom closer, quantum uncertainty crashes directly into gravity. The fabric of space-time itself begins to shimmer and flicker like static across a cosmic screen. Settle yourself, breathe slowly, and allow your curiosity to stay awake while your body relaxes as we begin this gentle journey through the universe. Now we drift into the first question. What truly breaks when we try to see smaller and smaller pieces of the universe? If we could keep zooming inward forever, beyond atoms, beyond protons, beyond even the tiniest quarks, would the universe keep revealing new layers of structure? Or would it eventually fade into darkness? This is not imagination. It is a real question that physics has tried to answer for more than 100 years. Each time, humanity has developed a better way to explore the microscopic side of the universe, from the first glass lenses to the largest particle accelerators ever built. We have followed the same principle. To see smaller details, we must use higher energy. That is how the universe allows deeper observation. Light, like all waves, can only reveal objects larger than its own wavelength. The light visible to our eyes, spanning from red to violet, has wavelengths hundreds of nanometers long. That is about 1,000 times wider than an atom. For this reason, even the most powerful optical microscope cannot show individual atoms. To move beyond that limit, scientists turn to electrons instead of light. An electron also behaves like a wave, but its wavelength can be made much shorter by accelerating it to very high speeds. In 1931, the German physicist Ernst Ruska built the first electron microscope, proving that we could see far beyond the limits set by visible light. By carefully adjusting the energy of electrons, he produced waves small enough to reveal the structure of cells, crystals, and even individual molecules, opening a new window into the hidden layers of the universe. 3 decades later, at the Stanford Linear Accelerator Center in California, scientists pushed this idea to its extreme. They fired electrons at protons with enormous energy, reaching tens of billions of electron volts. The way those electrons scattered revealed something unexpected. The proton was not a solid object. It contained smaller components within it called quarks. This experiment, known as deep inelastic scattering, became one of the most important discoveries in modern physics. It showed that matter itself had another hidden layer beneath what we once believed was fundamental. From that moment on, a simple rule of nature became clear. To explore smaller distances in the universe, higher energies are required. To see inside an atom, you need energy in the range of hundreds of electron volts. To look inside the nucleus, you need billions. To search for anything smaller than a quark, the energy required becomes almost unimaginable. But here the universe sets a trap. When we concentrate more and more energy into a smaller and smaller region, we begin to bend the very stage we are observing space-time itself. Einstein taught us that energy and mass are two expressions of the same reality. When too much energy is packed into a tiny space, it creates a gravitational field so strong that space-time curves around it. At first, this curvature is gentle and nearly invisible, but if we keep increasing the energy and keep trying to zoom in, something extraordinary happens. The energy density becomes so extreme that it collapses under its own gravity. The region we are trying to observe disappears behind an invisible boundary. In that moment, our microscope has created a miniature black hole. This is the point where the universe turns off the light. Beyond this threshold, no instrument can see further, because nothing, not even light, can escape the gravity that has formed. Physicists can estimate where this limit occurs, and it is called the Planck length. It is about 1.6 times 10 to the power of minus 35 meters, a number so small it challenges imagination. To put this into perspective, within the universe, if you enlarged a proton until it was the size of the Earth, the Planck length would still be smaller than a single atom on that Earth. At this scale, space and time are no longer smooth and continuous. They ripple and fluctuate like a violently boiling surface, a restless state that John Wheeler described as quantum foam, where the universe itself becomes uncertain at its deepest level. Within this foam, the geometry of the universe is always in motion, twisting, stretching, and collapsing from moment to moment. At this depth, our everyday ideas of distance and time no longer hold together. To truly reach such a scale, we would need energies around 10 to the power of 19 giga-electron volts, which is 15 orders of magnitude beyond what the Large Hadron Collider can produce. Even if humanity built a particle accelerator as large as our entire galaxy, it still would not be sufficient. It appears that the universe has placed a protective barrier around its most fundamental structure. This is not merely a limitation of technology, but a fundamental law of nature itself. The Planck length serves as a universal boundary, the smallest unit of measurement that carries any physical meaning. Below this scale, the very ideas of space and time begin to dissolve and lose clear definition. This boundary marks the region where quantum mechanics and general relativity collide, and where a future unified description of the universe must eventually arise. The James Webb Space Telescope allows us to look deep into the cosmos and far back in time, observing galaxies as they existed more than 13 billion years ago. Yet when we turn our attention inward toward the structure of matter, we are also traveling through time, but in the opposite direction. With each deeper layer we uncover, we move closer to the universe's earliest physical moments. At nuclear scales, we glimpse echoes of the first seconds after the Big Bang. At the scale of quarks, we encounter the physics of the first microseconds. And at the Planck length, we approach the instant when space-time itself first emerged into existence. So what happens if we try to look even closer than that? Does space unravel into chaos, or does it reveal a deeper order that our current theories cannot yet describe? This question has occupied generations of physicists, from the earliest pioneers to the most modern thinkers. As once described at the Planck scale, the smooth fabric of space-time gives way to a restless quantum foam filled with subatomic turbulence. For now, this region remains beyond our reach, yet the Planck length stands as both a barrier and an invitation, marking the edge of everything we understand while hinting that something deeper lies beyond. When we attempt to zoom toward infinity, the universe does not respond with answers. Instead, it offers silence, a horizon drawn by its own fundamental laws. But if light itself cannot reveal the smallest truths of the universe, what if another tool can? This leads us forward. Why is it that light cannot see atoms while electrons can? If light is how we perceive the world and even the distant universe, why does it fail when we attempt to observe the basic building blocks of matter? Why can light not reveal an atom while a beam of electrons can? At first, this seems difficult to accept. We often think of light as the ultimate messenger, the source of every image we have ever known. From the glow of distant galaxies to the gentle reflection on a drop of water, light delivers the universe to our eyes. And yet when scientists tried to use light to peer inside the atom, they saw nothing at all. The limitation was not in the instruments, but in the nature of light itself. Every beam of light behaves as a wave, and a wave cannot resolve details smaller than its own wavelength. The visible light that reaches our eyes has wavelengths of about half a micrometer, which is 500 nanometers. Atoms, by contrast, are roughly 1/10 of a nanometer across. When visible light strikes atoms, it is like trying to read tiny letters using waves rolling across the surface of a swimming pool. The waves simply pass over the details without revealing them. To observe structures that small, we need waves with much shorter wavelengths, waves with finer ripples and tighter spacing. One might then assume that higher energy light such as X-rays would solve the problem. And in part this is true. X-rays with their much shorter wavelengths can reveal atomic scale structures, which is why X-ray crystallography became such a powerful tool. In 1912, X-rays were directed at a crystal of copper sulfate, and the resulting diffraction pattern revealed that atoms are arranged in precise repeating lattices. This marked the birth of structural physics and opened a new window into the atomic universe. However, a serious problem remained. When photons reach such high energies, they do more than simply observe atoms. They begin to damage and disrupt them. A photon with enough energy to match the scale of an atom carries more than 1,000,000 electron volts of energy. That amount is sufficient to ionize atoms, eject electrons, and even disrupt the crystal structure one is trying to observe. This is where electrons enter the picture, not as particles of light, but as matter that can behave like a wave. In the 1920 seconds, Louis de Broglie put forward a simple yet profound idea. He proposed that every moving particle has a wavelength just like light. The faster the particle moves, the shorter its wavelength becomes. He called this the matter wave. 2 years later, this unusual idea was confirmed by experiment. In 1927, at Bell Laboratories, a beam of electrons was fired at a nickel crystal, and a diffraction pattern appeared. This was a pattern that only waves can produce. It was as if the electrons briefly behaved like light rippling across the atomic grid of the crystal. That single observation transformed physics. It demonstrated that electrons, when accelerated to the right energies, could resolve structures at the scale of atoms. Even more importantly, they could do so without destroying what they were meant to reveal. An electron beam with an energy of just a few hundred electron volts has a wavelength short enough to distinguish atoms while leaving them intact. This is why electron microscopes soon replaced optical microscopes for exploring the smallest details of matter. In 1931, the first prototype of the electron microscope was built in Berlin. That design used magnetic lenses to bend and focus streams of electrons, producing enlarged images of the microscopic world. Only a few years later, it became possible to see viruses, cell membranes, and molecular structures that light could never reveal. There is a quiet contrast here. Light, which allows us to see distant galaxies and the vast universe, cannot see an atom, while electrons, the very substance of matter, can uncover its hidden geometry. The reason lies in the link between energy and wavelength. To make light waves small enough to match the size of an atom, photons must carry energies of around 1,2,000 electron volts, far greater than visible light. An electron, however, moving with only a few hundred electron volts, naturally has a wavelength of the same scale. For the same level of detail, electrons therefore require far less energy and cause far less damage. When placed side by side, the difference is striking. A photon must burn hotter and push harder, risking destruction just to show what an electron can reveal with ease. Despite all its beauty, light is simply too blunt a tool for probing atoms. That is why, in modern laboratories, scientists mapping atoms on surfaces or visualizing molecular structures do not rely on light. Instead, they use streams of electrons guided by magnetic fields and scanned across samples with nanometer precision. The image produced is not formed from reflected light, but from the interaction of waves that scatter and interfere, creating a picture governed by probability. The resolution of a modern transmission electron microscope can reach fractions of an angstrom, less than 1/10 of a nanometer. This is fine enough to distinguish individual columns of atoms inside a crystal. The smallest structures we have ever directly resolved are on the scale of a single hydrogen atom's diameter. All of this traces back to one simple principle: shorter wavelength reveals finer detail. Yet this process cannot continue forever, because as wavelength shrinks, energy rises, and beyond a certain point, that energy begins to bend space-time itself. If we continue trying to look closer, the very act of observation eventually gives way to gravity. This is why the electron microscope represents a careful balance. It sits between power and delicacy, strong enough to reveal atomic structures, yet gentle enough to preserve them. It stands as a quiet achievement of human ingenuity, showing that deeper understanding does not always require brute force. Similar ideas appear in space science as well. The James Webb Space Telescope observes the universe in infrared light, using longer wavelengths, not to see smaller objects, but to detect fainter and more distant ones. At the same time, particle physicists on Earth push toward shorter wavelengths and higher energies to examine the subatomic fabric of matter. Between these extremes lies a continuous range of vision stretching from the immense scale of galaxies to the tiny decimal depths of atoms. Within this range, light and electrons serve different purposes. Light shows us how the universe appears from the outside, its shapes, colors, and motion across space. Electrons reveal how matter is assembled from within, exposing its hidden internal structure. Each has its own limit and its own domain. This realization was once deeply counterintuitive. When the diffraction pattern was first observed in 1927, it was met with disbelief. Electrons were expected to behave like particles, small charged projectiles, not waves of probability. Yet the pattern was unmistakable. It mirrored the interference fringes of light. In that moment, the boundary between what exists and how we observe it began to blur. This strange dual behavior was later described as the central mystery of quantum mechanics. The idea was that nature does not behave in the simple everyday way we expect. When scientists tried to use light to observe matter, they discovered that matter itself behaves like a kind of light, a wave, with its own frequency and pattern. Through this realization, humanity gained the ability to observe parts of the universe that light alone could never reveal. Electrons can see atoms while light cannot, because nature allows matter to reveal itself through motion and rhythm, through waves created by movement rather than illumination. At the atomic scale, that rhythm belongs to electrons. Yet as our view sharpened, another mystery emerged. If atoms have internal structure, what about their centers? Do protons and neutrons also contain something deeper? This question began to trouble physicists in the late 1960s. For many decades, protons and neutrons had been considered the solid core of every atom, the fundamental building blocks of matter. But subtle experimental clues suggested that these building blocks might not be solid after all. Something smaller might be hidden within them. By that time, the basic picture of the atom was already clear. Atoms were known to be mostly empty space, with a tiny dense nucleus surrounded by a cloud of electrons. This had been demonstrated in 1911, when alpha particles were fired at thin gold foil and most passed straight through. Only a few were deflected backward, revealing that nearly all of an atom's mass was packed into a nucleus only 100,000th of its diameter. The result was so surprising it was compared to firing a shell at tissue paper and having it bounce back. More than 50 years later, scientists wanted to push further and ask whether even that dense nucleus was truly solid or whether it too had an inner structure. To answer this, they needed a tool far more precise than alpha particles and energies far beyond anything previously used. That tool appeared at the Stanford Linear Accelerator Center in California. Completed in 1966, it was a remarkable achievement for its time. A straight tunnel about 2 miles long built to accelerate electrons to nearly the speed of light. By the standards of the 1960 seconds, it was a machine of extraordinary ambition capable of probing the deepest layers of matter ever explored. Electrons were chosen because they are point-like with no known internal structure of their own. When they scatter from a target, they act like tiny probes, revealing the shape and contents of whatever they strike. Each fast-moving electron became a microscopic radar pulse, mapping the unseen interior of matter. The idea was bold but clear. Fire electrons with energies of tens of billions of electron volts into protons and neutrons and observe how they scatter. If the nucleus was smooth and solid, the electrons would scatter evenly. But if smaller components were hidden inside, the scattering would be irregular and sharp. This reasoning led to one of the most important experiments in modern physics, known as deep inelastic scattering. The collisions were called inelastic because they were violent. The electrons did not simply bounce off the surface. They struck with such force that energy was transferred deep inside the proton. When the first data arrived around 1968, it defied expectations. The scattering did not match the behavior of a solid sphere. Instead, the electrons deflected as if they were hitting smaller point-like objects inside the proton. The pattern was unmistakable. Inside each proton appeared to be 3 distinct concentrations that resisted the electrons most strongly. These became the first experimental signs of quarks particles that had previously existed only as theoretical ideas. They had been proposed to explain the growing complexity of particles seen in earlier experiments, but no one had directly observed them before. Now the evidence was clear. Protons and neutrons were not fundamental after all. They were composite objects, each made of 3 quarks bound together by extremely powerful forces. This discovery reshaped our understanding of matter and by extension the universe itself, revealing that even the smallest building blocks hide deeper layers waiting to be uncovered. These forces were later explained by a new framework known as quantum chromodynamics, the theory describing the strong nuclear force that operates throughout the universe. This force turned out to be unlike any other force we know. It becomes stronger the more you try to pull quarks apart, much like a rubber band that stretches tighter but never snaps. The energy required to separate quarks is so immense that new pairs of quarks are created before the originals can ever be isolated. This is why no one has ever observed a single free quark on its own. Instead, quarks are permanently confined inside larger particles called hadrons, such as protons, neutrons, and other particles made of 2 or 3 quarks. This discovery transformed our understanding of matter at the deepest level. The atomic nucleus, far from being a solid object, is mostly empty space threaded by intense energy fields. Inside it, quarks move within a dense cloud of gluons, the particles that carry the strong force and bind the nucleus together. These gluons are constantly appearing and disappearing, exchanging energy at speeds close to that of light. If we could somehow look inside a proton, it would not resemble a rigid sphere at all. It would appear alive like a restless storm of quantum motion, a churning sea of virtual particles forming and dissolving billions of times each second. This hidden activity plays out everywhere in the universe, from the atoms in your body to the matter inside distant stars. Experiments conducted after those early discoveries refined this picture with remarkable precision. At major research centers, particle accelerators smashed protons together at ever higher energies. confirming that quarks behave almost like free particles when examined at extremely short distances. This property became known as asymptotic freedom. Yet as soon as quarks begin to separate, the strong force tightens again, pulling them back into confinement. This behavior is unique in all of physics. Most familiar forces such as gravity or electromagnetism grow weaker as objects move farther apart. The strong force does the opposite. It guarantees that quarks can never escape the bound structures that form matter. Paradoxically, this permanent confinement is exactly what makes the universe stable. The strength of the strong force holds protons together for billions of years, longer than the age of the universe itself. It is the reason atoms can exist, the reason stars are able to burn and shine, and the reason you listening right now are here at all. The energy scale required to probe these depths, around 1 billion electron volts, corresponds to distances of roughly 1 quadrillionth of a meter. At this scale, the clear line between solid and empty begins to blur. Matter appears to be mostly nothing, held together by invisible energy that binds emptiness into structure. Even today, the legacy of those early accelerator experiments remains one of the clearest demonstrations of how we learn about the universe. We hurl particles at particles and read the nature of reality by studying how they recoil. It is like striking a bell in total darkness and learning its shape by listening to the echoes. Yet even the quark may not represent the final layer of matter. Some physicists suspect that even smaller entities could exist beneath quarks, though no experiment has yet confirmed this. The search continues, but each step deeper demands energies far beyond our current reach. As was once observed about these discoveries, the world turned out to be more complex and more fascinating than anyone had expected. That insight remains true today. Each time we peel back another layer of nature, the universe reveals an even deeper mystery waiting below. And as our machines grow more powerful, the questions only multiply. If we continue increasing energy and colliding protons more violently, will we eventually reach a point where even the strong force gives way to something entirely new? That question defines the next frontier. When our instruments reach energies of trillions of electron volts, will we merely see more quarks, or will something stranger emerge? This leads directly to the next challenge. Can the Large Hadron Collider truly penetrate the veil of the Higgs field? What happens when humans build a machine powerful enough to disturb the vacuum of the universe itself? Can it actually reveal deeper layers of reality, or does it only create brief disturbances that vanish almost instantly? That question lies at the heart of the Large Hadron Collider, the most ambitious scientific instrument ever constructed. Many imagine it as a dangerous weapon or as a ring of unimaginable energy buried beneath the border between France and Switzerland. In reality, the Large Hadron Collider is more like a colossal microscope, a silent eye that uses no glass or lenses, only magnetic fields and protons racing close to the speed of light. Its purpose is simple in concept, but extraordinary in practice: to see deeper into the structure of the universe than any human tool ever has. The collider accelerates 2 beams of protons in opposite directions around a circular tunnel 27 kilometers long. Each beam carries particles energized to about 7 trillion electron volts. When the beams collide head-on, the total energy of the impact reaches 14 trillion electron volts. This value was chosen with care. It lies near a theoretical threshold where the Higgs field, the invisible field that gives mass to matter throughout the universe, can be disturbed strongly enough to produce a detectable ripple known as the Higgs boson. When physicists say the collider can see the Higgs, they do not mean it observes the field directly. Instead, it taps the field much like striking the surface of a pond to reveal a brief wave that quickly fades away. When those protons collide, their energy is squeezed into a region smaller than the nucleus of an atom, recreating conditions that last existed less than a trillionth of a second after the Big Bang. For a brief moment, the vacuum of space behaves in an unfamiliar way. Particles flicker into existence and vanish again. Energy transforms into mass, and mass returns to energy, echoing the same processes that shaped the newborn universe. To understand why the Large Hadron Collider is truly a microscope of the universe, rather than just a machine for collisions, we need to recall one simple rule that connects the largest scales of the cosmos with the smallest. The higher the energy, the smaller the distance we can explore. This principle guides modern physics. Each increase in energy sharpens our view of the microscopic universe. With visible light, humanity learned to see cells. With electrons, we uncovered atoms. With beams at the level of giga electron volts, we revealed quarks. And now, with energies measured in tera-electron volts, we can disturb the very fields that allow quarks to exist at all. Inside the Large Hadron Collider, each proton is steered by 1232 superconducting magnets cooled to about 1.9 Kelvin, colder than the natural temperature of outer space. The vacuum inside the beam pipe is emptier than the space between stars. Every component, every pulse, every magnetic curve is engineered to keep the beams aligned within a fraction of a millimeter. When the protons finally collide, they do so inside detectors as large as buildings. ATLAS, CMS ALICE and LHCb. Vast instruments designed not to destroy matter but to listen carefully to what the universe reveals. ATLAS and CMS, the two largest detectors, made it possible to identify the Higgs boson in 2012. Each collision is tracked by millions of sensors. Out of more than 1 billion collisions every second, only a handful produce the distinctive decay patterns that signal a Higgs event. Even then, those traces last for less than 1/trillionth of a second before dissolving into other particles. When the Higgs boson was confirmed, it marked more than a single discovery. It demonstrated that the standard model, the framework describing all known particles and forces, was complete in a deep and meaningful way. Yet an even larger question remained. How deep can the Large Hadron Collider truly see? If we treat it as a cosmic microscope operating at 14 tera-electron volts, it can probe distances down to about 100 billionth of a meter, roughly 1/10 of a femtometer. This scale is smaller than the radius of a proton approaching the realm where quarks and gluons swirl in constant confinement. At this depth, we are no longer just observing particles, we are exploring fields, continuous backgrounds that fill the entire universe. The Higgs field, the electromagnetic field, and the strong and weak nuclear fields are not objects placed inside space. They are space itself in motion. Each collision inside the Large Hadron Collider sends ripples through these fields, revealing how they interact. Yet, even with all its power, the collider remains far from the energy needed to reach the Planck scale, the ultimate limit discussed earlier. To reach that boundary, protons would need energies not of 7 tera-electron volts, but of 10 billion trillion electron volts, requiring a machine the size of an entire galaxy. For this reason, the Large Hadron Collider is not the final microscope of the universe. It is a bridge, the sharpest tool humanity currently possesses between what is known and what remains unknown. Its discoveries extend beyond physics into how we understand reality itself. When energy is pushed high enough, we do not simply see smaller structures. We create entirely new ones. This is what makes the Large Hadron Collider unlike any instrument before it. It does not merely observe the universe, it briefly recreates fragments of it from pure energy. The detectors capture these moments with extraordinary precision. Each proton collision produces sprays of particles, photons, and neutrinos that burst outward. Advanced algorithms then trace these fragments backward, reconstructing what occurred at the exact instant of impact. It is like hearing pieces scatter across a floor and deducing the shape of the object that fell by sound alone. The resulting data are so vast and complex that they require computing systems spread across the planet, forming the worldwide Large Hadron Collider grid that links hundreds of institutions in more than 40 countries. Every second of operation generates more data than an entire human lifetime of internet use. Each piece is filtered, analyzed, and compared with theoretical predictions. This global collaboration of thousands of scientists stands as one of humanity's quiet achievements, cooperation on a planetary scale to understand the smallest components of the universe. There is something deeply moving in that precision, not poetic but profound. Since the discovery of the Higgs boson, the Large Hadron Collider has continued its exploration. It has searched for supersymmetric particles, heavier relatives predicted by extensions of the standard model, but none have yet appeared. It has studied rare particle decays, searched for clues to dark matter, and measured the strong force between quarks at energies never reached before. With each new run, improvements are made. Higher luminosity, more collisions per second, clearer data, and deeper insight into the universe. The upcoming high-luminosity Large Hadron Collider will expand this reach even further, testing whether nature hides surprises at scales we have not yet seen. Yet beyond all the technology, one quiet question remains in every control room. If we have now seen the Higgs, what comes next? If the standard model is complete, why does the universe still feel unfinished with dark matter, dark energy, and gravity itself standing apart? Perhaps the answer lies just beyond the reach of 14 tera-electron volts. Perhaps we must go higher to energies of hundreds or even thousands of tera-electron volts to reach the next threshold and uncover the next hidden layer of reality in the universe. Or perhaps the clues are already present in the data waiting quietly to be recognized. After the discovery of the Higgs, it was said that a great milestone had been reached, yet it marked a beginning rather than an ending. That is exactly what the Large Hadron Collider represents. Not a final answer, but a doorway. The sharpest eye humanity has ever created. It is an eye that does not look through glass, but through energy itself. A machine that allows us to watch the universe replay its earliest moments, one collision at a time. But what happens when even this immense energy begins to press against a deeper law of nature? What happens when our desire to see more causes gravity itself to respond? What if the closer we look into the universe, the more the universe pushes back? What if instead of revealing finer detail, nature begins to collapse under the weight of our curiosity? This is not imagination. It is the quiet response of gravity, a limit woven into the structure of space and time. At first, the idea sounds strange. How could simply looking too closely lead to the creation of a black hole? Yet this is exactly what occurs when the energy used to observe becomes too intense. Every attempt to see smaller structures demands higher energy. To explore the atom, we accelerate electrons to energies of hundreds of electron volts. To look inside the nucleus, we use energies of billions. The rule is straightforward. Finer detail requires shorter wavelengths, and shorter wavelengths require higher energy. But this is where the universe turns that rule back on us. The more energy we concentrate into a tiny region of space, the more that energy bends space-time itself. General relativity tells us that energy, just like mass, creates gravity. Each time we increase the power of our microscopic vision, we also strengthen the gravitational field within the region we are examining. At first, this effect is incredibly small, almost imperceptible. But as we move beyond atomic scales into the realm of quarks and gluons, the energy density rises to astonishing levels. Eventually, a delicate balance is crossed. The energy used to probe a region becomes so concentrated that the gravity it generates traps light. The region we are trying to observe forms its own event horizon. This is gravity pushing back. It is the moment when looking too closely causes everything to disappear. In simple terms, if enough energy is compressed into a sufficiently small space, that region behaves as though it has mass. When the gravity produced by that mass becomes strong enough, it creates a boundary beyond which light cannot escape. This boundary is known as the Schwarzschild radius. When the size of the region being examined shrinks to the same scale as this radius, the experiment reaches its end. The microscope effectively becomes a black hole. Beyond this point, adding more energy does not reveal smaller detail. It only enlarges the black hole. This is the ultimate limit of observation, the cosmic version of diminishing returns. It tells us that nature has a smallest, meaningful length, around 1.6 times 10 to the power of minus 35 meters, known as the Planck length. At this scale, the gravitational radius created by the energy equals the size of the region itself. Any attempt to focus more sharply causes the entire experiment to collapse. For perspective, the protons inside the Large Hadron Collider reach energies of about 7 trillion electron volts, allowing us to probe distances down to roughly 1/10 of a femtometer. To reach the Planck length, we would need energies a trillion times greater, around 10 to the power of 19 giga electron volts. That is more energy than all the stars in the observable universe could produce compressed into a single point. The universe shields its smallest scales behind a curtain of gravity. The closer we try to look, the tighter that curtain draws closed. This is not a failure of technology, it is a fundamental feature of space-time itself. Physicists often describe this interaction as a tension between quantum mechanics and gravity. Quantum mechanics urges us to look closer to sharpen measurements and concentrate energy. Gravity resists bending space-time until the idea of position itself breaks down. What began as a theoretical curiosity has deep consequences for how we understand the universe. It tells us that there is a boundary not only to what we can build, but to what can physically exist beyond that limit. Our current laws of physics can no longer describe what happens there. To sense how extreme this boundary is, imagine zooming in on a proton. Now imagine zooming in 1 trillion times further. You arrive at the Planck scale, where distance loses meaning and space and time fluctuate like foam. At this level, gravity and quantum effects are equally powerful, and neither can be ignored. This boundary, where energy, gravity, and measurement meet, is often described as the black hole barrier. No matter which method we try, any attempt to see beyond it causes gravitational collapse. The very act of observing creates the barrier it cannot cross. This is not merely an abstract idea. The same reasoning explains why black holes exist throughout the universe. When a massive star collapses, its mass is squeezed into such a small region that its gravitational radius becomes larger than its actual size. Light can no longer escape and the core of the star vanishes behind a horizon. In our case, the same principle applies not to stars in space, but to experiments carried out here on Earth. As we approach this critical gravitational radius, the laws of physics push back more and more strongly. That resistance defines the Planck scale. It is not a wall in the ordinary sense, because nothing physical blocks the view. Instead, it is a limit built into the geometry of reality itself. At this boundary, distances, time intervals, and even the difference between inside and outside begin to lose meaning. In this way, gravity's response is not destructive, but protective. It prevents us from accidentally tearing the universe apart. It keeps energy, matter, and space-time in balance. Yet this same limit leaves us with an unanswered question. If we cannot see beyond this boundary, how can we ever know what space-time is made of at its deepest level? Are we forever locked outside the most fundamental layer of reality? This question drives the search for a theory of quantum gravity, a framework that would unite general relativity with quantum mechanics. The hope is that such a theory will describe how space-time behaves when it becomes as small and as turbulent as the particles within it. Some ideas suggest space-time might be built from discrete loops forming a network at the smallest scales. Others imagine tiny vibrating filaments, where oscillations replace the chaos of collapsing space-time. Until such a theory is complete, this paradox remains. The closer we try to look, the more gravity bends our window closed. The harder we push to uncover the foundations of the universe, the more the universe conceals them. Still, this balance between energy and gravity, between curiosity and collapse, is what keeps the cosmos stable. It is the quiet rule that prevents stars from imploding and atoms from tearing themselves apart. It defines not only the limits of knowledge, but the structure of existence itself. As we approach a black hole, time slows down and eventually appears to stop at the horizon. At the Planck scale, time itself may seem to pause, not because space ends, but because measurement no longer has meaning. Yet even this gravitational resistance opens one of the most fascinating frontiers in modern physics. It is the place where quantum theory and gravity must finally come together. Because if space-time collapses when we look too closely, what happens when quantum uncertainty is also included? This leads to the next question. Is the Planck length the final boundary of reality? Is there a smallest possible size in the universe, a scale below which distance itself stops making sense? Physicists call this boundary the Planck length, the point where the laws of nature as we understand them begin to unravel. This is not simply a problem of smaller rulers or stronger microscopes. It is a question of whether space itself can exist below a certain scale. To see why, consider how this strange number about 1.6 times 10 to the power of minus 35 meters arises. It was not discovered through experiment, but through reasoning. When three fundamental constants of nature are combined, the speed of light, the gravitational constant, and the quantum constant of action, they naturally form a unit of length. That length marks the scale where quantum mechanics and gravity become equally strong. Below it, neither theory can describe reality on its own. Smooth space-time and quantum probability collide, and both descriptions fail. To imagine how small this is, picture shrinking step by step. A human hair is about 1/10 of a millimeter wide. A red blood cell is 1,000 times smaller. A proton is 10 billion times smaller still. Now take that proton and divide its diameter by 10 billion again, and then repeat that division 30 times. That brings you to the Planck length. At this scale, space is no longer calm or continuous. It flickers and churns, its geometry twisted by quantum uncertainty and gravitational tension. Distances blur, and even the idea of before and after becomes uncertain. Space-time behaves like a restless foam dynamic and unstable, where tiny wormholes may open and close in trillionths of a second. Energy fluctuates violently, creating brief bursts of curvature that appear and vanish like bubbles in boiling water. What seems like empty space on human and cosmic scales becomes a storm at the Planck scale. The energy required to reach this realm is almost beyond imagination. This energy, known as the Planck energy, is roughly 10 to the power of 19 giga-electron-volts. By comparison, the Large Hadron Collider, the most powerful machine humanity has built, reaches only 14 tera-electron-volts, a difference of 15 orders of magnitude. To build a particle accelerator capable of reaching the Planck energy, it would need to stretch across several thousand light-years. This is not just beyond our technology, but beyond what the universe itself allows. The limitation is not an engineering problem. It is a fundamental rule of reality, because at such extreme energies, the gravitational pull created by the energy would immediately collapse into a black hole. The instant we tried to measure something smaller than that scale, space-time itself would close in around it. Nature draws a curtain not made of matter but of meaning. Physicists have long debated what this curtain truly represents. Some see it as a hard wall, the smallest possible unit of space like pixels on a cosmic screen. Others see it as a boundary, a smooth transition into a deeper realm where gravity and quantum physics become one. Either way, this is the point where our equations begin to quietly say, you cannot go any further. There is a strange elegance in that precision. From the Planck length, we can also define the Planck time, the shortest possible moment that can still be meaningfully described, about 10 to the power of minus 44 seconds. Below this, the usual flow of cause and effect begins to blur. Time no longer moves in the way we recognize. These scales mark the earliest chapter of the universe itself, the instant just after the Big Bang, before the laws of physics settled into the forms we know today. Space missions have mapped the faint afterglow of that era known as the cosmic microwave background, but they can only see back to when the universe was roughly 3,000,000 years old. The Planck era ended much earlier, when the universe was less than a trillionth of a second old. At that moment, everything we know today, matter, energy, even the shape of space itself, was still tangled together. Forces had not yet separated. The Higgs field had not yet formed. The universe was smaller than an atom, yet it already carried the seeds of all future galaxies. The Planck scale, then, is not just a number. It marks the edge of our cosmic memory. It is where known laws stop working and something deeper must take over. To move beyond it, new ideas are required. This is why theories like string theory and loop quantum gravity exist. They are not flights of imagination, but serious attempts to describe what happens when space-time itself is no longer smooth and continuous. String theory suggests that what we think of as point particles are actually tiny vibrating loops of energy, each about the size of the Planck length. Loop quantum gravity proposes something different, that space itself is built from discrete units, tiny quanta of area, and volume linked together in a vast network. Although these theories differ, they share one profound conclusion. Below the Planck scale, distance itself stops being a meaningful concept. You cannot speak of half a Planck length any more than you can speak of half a photon. It is not merely too small to measure. It has no definition. This makes the Planck length not a wall we might someday cross, but a horizon that can never be passed. It is a fundamental boundary between what can physically exist and what can only be imagined. It is the smallest tick mark on the ruler of reality. Yet there is a quiet irony here. The constant that defines the Planck length, the gravitational constant, is the least precisely measured of all the fundamental constants. We know the speed of light and the quantum constant with extraordinary accuracy, but gravity still resists precise measurement. This means that the most fundamental scale in physics depends on the force we understand the least. Even so, the idea of a minimum length has powerful consequences. It implies that there is a limit to how much information the universe can store within any given region of space. According to the holographic principle, the total information contained inside a region depends not on its volume but on the surface area, measured in Planck units. In this view, reality itself may be pixelated at the smallest scale, with each pixel holding a single bit of information. This idea lies at the heart of modern black hole physics. When it was discovered that black holes emit radiation, the rate of that radiation depended on the Planck area, the square of the Planck length. This was one of the first clues that the universe at its deepest level might count information in Planck-sized pieces. Whether the Planck length marks the true end of reality or the doorway to something deeper remains unknown. It is the smallest scale we can currently define. Whether space itself is truly quantized remains one of the most profound open questions in science. It is a humbling realization. Every measurement we make and every law we write assumes that space and time are continuous. If they are not, if reality is built from discrete Planck-sized building blocks, then our picture of the universe is only an approximation. At the Planck scale, space may not be smooth at all, but woven from tiny loops of gravity forming a vibrating foundation beneath everything we observe. And if the Planck length is truly the final boundary of the visible universe, then what lies beyond may not be smaller but entirely different. Space and time themselves may be emergent, arising from something even more fundamental. This leads directly to the next mystery. If there is a minimum distance, does the uncertainty principle itself change once gravity becomes part of the picture? Does quantum uncertainty gain a gravitational layer? If every photon we use to measure space also bends that space, then what does precision really mean? This question sits at the heart of one of the most subtle challenges in modern physics, understanding how quantum uncertainty behaves when gravity joins the game. Heisenberg's uncertainty principle emerged in the 1920 seconds, when it became clear that in quantum mechanics, it is impossible to know both the position and the momentum of a particle with perfect accuracy. The more precisely you determine where something is located, the more uncertain its motion becomes, and the more accurately you measure its momentum, the more its position begins to blur. At the smallest scales of the universe, reality refuses to stay still when we observe it. This is not a weakness of our instruments. It is a fundamental property of nature itself. Even in an ideal laboratory, even with flawless technique, this uncertainty cannot be removed. It is as though the universe hides its exact coordinates behind a gentle veil of probability. Yet Heisenberg's principle, elegant and powerful, was originally formulated for a universe without gravity. It describes the quantum realm where energy and probability interact, while the structure of spacetime remains fixed in the background. Once gravity enters the picture, once energy itself is allowed to curve spacetime, that balance begins to shift. Imagine trying to locate an electron using light. You shine a photon, a particle of light, with a specific wavelength toward it. If the wavelength is long, you cannot resolve details smaller than that wave. So you choose photons with shorter and shorter wavelengths, meaning higher and higher energy to sharpen your view. But eventually, the photon becomes so energetic that its own gravity can no longer be ignored. That single photon now carries enough energy to slightly distort spacetime around the region you are observing. The act of measurement bends the very coordinates you are trying to measure. If you continue increasing the energy, the distortion becomes stronger. At an extreme point, the energy density of the photon would be sufficient to form a tiny gravitational well, a miniature black hole appearing exactly where you attempted to make a measurement. Instead of seeing finer detail, you lose all information. This idea leads to what physicists call the generalized uncertainty principle. It states that Heisenberg's original rule must be adjusted when gravity becomes significant. At low energies, ordinary quantum behavior applies. The more precisely you know a particle's momentum, the less precisely you know its position. But as energy increases and gravitational effects grow, something unexpected happens. The uncertainty in position stops decreasing. It reaches a minimum value and then begins to increase again. In simple terms, there exists a smallest measurable distance in the universe. Beyond that point, trying to look closer actually makes your vision less precise. That minimum distance corresponds to the Planck length, about 1.6 times 10 to the power of minus 35 meters. This result does not come from telescopes or particle accelerators, but from reasoning about how measurement, energy, gravity, and spacetime interact. Its elegance lies in how it connects two of the strongest pillars of physics, without forcing them into a single theory. From the quantum perspective, we have a rule that limits precision. From the gravitational perspective, we know that energy curves spacetime. The generalized uncertainty principle is where these two truths meet naturally and inevitably. It tells us that even if we never build a machine capable of reaching Planck energy, the universe already enforces its own boundary through the structure of spacetime itself. It does not allow information to be compressed into a region smaller than that scale. This gravitational refinement of Heisenberg's idea has guided decades of research. In string theory, for instance, it appears automatically. Strings which replace point particles as the fundamental elements of reality resist being squeezed. The more energy you add, the more they stretch and vibrate, spreading out rather than collapsing inward. Once again, the universe protects its smallest structures. A similar conclusion appears in loop quantum gravity, a theory that treats spacetime itself as quantized. In that view, distances and areas come in discrete units, indivisible chunks roughly the size of the Planck length. Below that geometry, as we understand it, no longer exists. This may sound abstract and far removed from observation, but its traces appear subtly in black hole physics. When black hole radiation was studied, it was found that temperature and entropy depend on surface area measured in Planck units. This connection between information gravity and quantum uncertainty suggests that the generalized uncertainty principle is not merely mathematical but physical. It also reshapes how we think about information in the universe. If there is a smallest possible length, then there is also a smallest unit of information, a fundamental bit tied to that scale. Every black hole and every region of space carries a finite amount of information proportional to its surface area. In this view, the universe stores information not in its volume but along its boundaries. This simple idea links black holes, holography, and quantum uncertainty, three of the deepest concepts in modern physics, all pointing toward the same conclusion. There is a natural limit to what can be known about the universe, not because our instruments are weak, but because the universe itself is constructed with that limit built in. To see how strange this boundary truly is, imagine a simple experiment. Suppose you try to measure the exact position of a particle with extreme precision. You choose higher energy light, shorter wavelengths, and more sensitive detectors. At first, your measurement becomes more accurate, but after a certain point, increasing the energy further causes a new problem. The gravitational field of the photon you use to measure begins to bend the particle's path, adding uncertainty instead of removing it. If you continue pushing this process far enough, you would eventually create a gravitational horizon around your own experiment. It would be as if the very act of asking where something is sends a ripple so strong that space itself refuses to respond. In a way, large-scale observations of the universe echo this same idea. When the James Webb Space Telescope observes distant galaxies, it is not only seeing light from the early universe, but also probing how space-time stretches as the universe expands. At the opposite extreme, theoretical physicists perform similar explorations using thought experiments, pushing the laws of measurement until they begin to fail. Both approaches, the cosmic and the quantum, converge on the same question: is there a smallest unit of space? The generalized uncertainty principle suggests that there is, though not as a sharp wall. Instead, it resembles a hazy horizon where precision in position and momentum trade places and blend together. At this boundary, the universe is neither fully continuous nor completely discrete. It exists in a strange middle state. The uncertainty principle, first discovered in the behavior of electrons, unexpectedly reaches all the way to the structure of space-time itself. Uncertainty, when gravity becomes part of the picture, is no longer just a blur in measurement. It becomes part of the architecture of reality. If there truly is a smallest measurable distance, then a deeper question follows. What is the nature of the things we are measuring? If matter behaves like waves, and space itself may be quantized, perhaps the fundamental building blocks of the universe are not points at all. This question led to one of the most ambitious ideas in modern physics: string theory. By the late 20th century, physicists had pushed their equations to the breaking point. Quantum mechanics successfully described the smallest scales. General relativity governed the largest structures of the universe. But near the Planck length, both theories began to fail. Every attempt to combine them produced infinities numbers so large that the equations no longer made physical sense. The problem was not with telescopes or particle colliders. It was with the way matter itself was being described. For decades, elementary particles were treated as points objects, with no size or shape, only position and charge. This simplification worked remarkably well at everyday energies. But at extremely high energies close to the Planck scale, it led to a crisis. When two point-like particles collide at such energies, all their energy is forced into an infinitely small location. The mathematics breaks down. Gravity becomes infinite. So, physicists began to ask a different question. What if the fundamental objects of the universe are not points but strings? These strings would be one-dimensional filaments, incredibly small, with lengths on the order of the Planck length, about 10 to the power of minus 35 meters. If particles were tiny vibrating loops instead of dots, the problematic infinities might disappear. The energy of a collision would be spread along the length of the string rather than collapsing into a single point. When this idea was explored mathematically, something remarkable happened. The infinities vanished. Gravity did not destroy the equations. It emerged naturally from them. In string theory, gravity is not added as an extra ingredient. It arises automatically from the way strings vibrate and interact. At low energies, these strings behave just like particles. Their vibrations are so subtle that they appear point-like to us. But as energy increases and we try to zoom in further, the picture changes. Instead of revealing sharper detail, the strings begin to vibrate more intensely, developing new patterns of motion. Their effective size grows rather than shrinks. This behavior mirrors what we see with gravity and the generalized uncertainty principle. When we attempt to measure with greater precision by adding energy, the result is not clarity but blur. String theory embraces this effect and places it at the foundation of matter itself. At energies far beyond anything humans can produce, far beyond any collider we could ever build, strings cannot be squeezed into something smaller. The more energy we add, the more they stretch and vibrate, ensuring that the universe never allows infinite sharpness at its deepest level. A string cannot be compressed to a size smaller than its own length. The more energy you apply, the more the string stretches and vibrates in higher and higher modes. Like a guitar string pulled tighter and tighter, the clarity of detail stops improving. Nature simply refuses to allow sharper resolution. From this behavior, a striking idea emerges. In string theory, there is a smallest measurable distance roughly equal to the length of the string itself, close to the Planck scale. Below this point, the word distance loses its meaning, not because the universe ends, but because the methods we use to define space no longer function. The path that led to this idea reflects both human curiosity and mathematical necessity. String theory did not begin as a grand explanation of the universe. It first appeared in the late 1960s as a model to describe the strong nuclear force, the force that binds quarks inside protons. Physicists studying particle collisions noticed that certain energy patterns could be described as vibrations of an extremely small string. Then, an unexpected feature appeared in the equations. One vibration mode behaved exactly like a graviton, the hypothetical quantum particle responsible for gravity. That single result transformed everything. String theory was no longer limited to the strong force. It suddenly offered a way to describe all fundamental forces: electromagnetism, the weak nuclear force, the strong nuclear force, and gravity, all unified through the geometry of vibrating strings. Each vibration of a string corresponds to a different particle, much like different notes produced by a musical instrument. The electron, the photon, and the Higgs boson can all be understood as distinct harmonics of one underlying structure. In this view, the universe behaves like a vast symphony of vibrating strings, with the laws of physics acting as the melodies that govern their motion. While this image may sound poetic, the mathematics behind it is precise and demanding. String theory requires additional dimensions beyond the familiar 3 of space and 1 of time. In total, there may be 10 or 11 dimensions, most of them curled up so tightly that they remain invisible. These hidden dimensions control how strings vibrate, and therefore determine which particles can exist in our universe. The shapes of these hidden dimensions are known as Calabi-Yau, manifolds, complex geometric forms that twist and fold beyond everyday intuition. Each possible shape corresponds to a different version of the universe, with its own physical laws. The number of possible shapes is estimated to be around 10 to the power of 500, a figure so large it defies comprehension. At this stage, string theory becomes more than a solution to mathematical infinities. It becomes a vast landscape of possible universes. Yet at its core, it still answers a simple and profound question. Why can we not zoom inward forever? Because in a universe built from strings, infinite sharpness does not exist. The finite length of a string defines the smallest possible scale. Beyond that limit, adding more energy does not reveal finer detail. Instead, it excites new vibrations and resonances. The image does not sharpen, it changes tone. This built-in softness prevents the fabric of the universe from tearing itself apart. In theories based on point particles, collisions at extreme energies produce infinite curvature and singularities. In string theory, those singularities are smoothed away because strings have size. Energy never collapses into a single point. As a result, space-time remains stable, and gravity naturally emerges from this smoothing. When strings vibrate and interact, one specific mode behaves exactly like the gravitational field described by general relativity. Gravity is not added as an extra feature. It appears inevitably from the mathematics. This is why physicists often say that in string theory, gravity falls out of the equations. The universe does not need gravity inserted by hand. It is already present, encoded in the motion of every string. This realization brings an unusual harmony to physics. For the first time, quantum mechanics and gravity exist together without conflict, not as competing ideas but as expressions of the same geometric structure. Space-time, energy, and vibration become parts of a single language. Direct experimental tests remain beyond our reach, since the energies needed to probe strings near the Planck scale far exceed any experiment humanity can build. Still, indirect signs may one day appear. Subtle patterns in the cosmic microwave background from the early universe, ripples in space-time, or exotic particles predicted by supersymmetry could offer hints of this hidden framework. Until then, string theory stands as an extraordinary attempt at unification. A theory not yet confirmed, yet remarkably consistent, offering a vision in which the deepest layer of the universe is not chaos or a barrier, but an underlying rhythm. It has been said that string theory is more than just a theory about tiny strings. It is a broad framework that brings gravity and quantum mechanics together as parts of a larger picture of the universe. That larger picture may explain why space-time does not rip apart when we investigate extremely small scales, and why nature's finest details shimmer rather than break. Yet there is another idea, one that may be even more unusual. What if space itself is not smooth and continuous, but instead made from discrete quantum building blocks, tiny units of area and volume woven together by the very spin of space-time? This question leads us to one of the most intriguing approaches in modern physics: loop quantum gravity. It begins not with vibrating strings, but with geometry itself. Where string theory imagines the universe as a symphony of energy loop, quantum gravity describes it as a network made from quanta of space. To understand why this idea matters for the universe, we must return to a problem left unresolved by Einstein. His general theory of relativity tells us that gravity is not a force pulling across distance, but the curvature of space-time caused by mass and energy. Planets follow curved paths, and light bends as it travels through the cosmos. At large scales, everything appears smooth and continuous within this elegant structure. But when we zoom down to the smallest scales near the Planck length of about 1.6 times 10 to the power of -35 meters, that smoothness begins to fail. Quantum fluctuations disturb space-time like waves on a restless sea. The continuous surface described by relativity no longer holds. Loop quantum gravity takes this breakdown seriously and treats it as a clue rather than a problem. Instead of adding new particles or hidden dimensions, this approach rewrites the very meaning of space. According to loop quantum gravity, space is not continuous, it is quantized. Just as light comes in discrete packets and energy appears in specific amounts, space itself is built from tiny, indivisible units. These smallest chunks of area and volume are unimaginably small, each on the order of the Planck scale. In this picture, the geometry of space-time forms a structure known as a spin network. Each node in this network represents a quantum of volume, and each connection between nodes represents a quantum of area. Together, they create the microscopic scaffolding of the universe. From far away, this network appears smooth, much like a beach looks smooth from a distance, even though it is made of countless grains of sand. Up close, however, continuity dissolves into discrete vibrating elements. This is a radical yet elegant idea. Space is built from loops. Closed loops of gravitational field lines interweave to form a fabric made of finite connected regions. Time itself is also quantized, advancing in tiny steps rather than flowing continuously. At the deepest level, reality ticks like a quantum clock. At the Planck scale, space is not continuous but granular, woven from loops of gravity. This is not merely metaphor. The theory rests on rigorous mathematics. By rewriting Einstein's equations in quantum form, physicists found that areas and volumes can only take specific values, similar to how electrons in atoms occupy discrete energy levels. You cannot have less than one quantum of volume. This means that even what we call empty space has structure. Space is not nothing. It has its own microscopic texture, a quiet web of quantum geometry that supports everything in the universe. At larger scales, this texture averages out, giving rise to the smooth space-time described by general relativity. Remarkably, Einstein's theory is not discarded. It emerges naturally when these quantum structures are viewed from afar. In the language of physics, general relativity appears as the low-energy limit of loop quantum gravity. In other words, the smoothness of space-time is an illusion of scale like mist that appears continuous until examined closely and revealed as countless droplets. This shift in perspective has profound consequences, especially for singularities, the points of infinite density predicted at the centers of black holes and at the beginning of the universe. In classical relativity, singularities signal the breakdown of equations. But in loop quantum gravity, the quantum structure of space prevents such infinities from forming. Space cannot be compressed beyond one quantum of volume. This suggests that the Big Bang may not have been a creation from nothing but a bounce, a transition from a previous universe that collapsed and then expanded again into the cosmos we observe today. This idea is often called the Big Bounce, and it arises naturally from the equations of loop quantum gravity. Satellites have observed the oldest light in the universe, the cosmic microwave background, giving us a picture of the cosmos as it existed about 13.8 billion years ago. These observations align beautifully with the predictions of general relativity, yet they cannot reveal what happened before that early moment. Loop quantum gravity suggests that something did exist before, but it was governed by quantum geometry rather than the smooth space-time we are familiar with. If this picture is correct, then every atom, every planet, and every galaxy in the universe is suspended within an immense network of quantum threads. Gravity, the flow of time, and even the shape of space itself emerge from how these loops twist, link, and interact. It is an idea that feels strange yet follows a clear logic. We already know that energy and matter come in discrete units. There is no obvious reason why space itself should be different. For now, experimental proof remains out of reach. The Planck scale lies far beyond what any telescope or particle accelerator can directly explore. Still, physicists continue to search for indirect signs. They look for tiny imprints in the polarization of cosmic light, or for subtle irregularities in the timing of gamma-ray bursts that have traveled across billions of light-years. If space-time truly has a granular structure, photons with different energies might travel at slightly different speeds, leaving behind a faint signature of that underlying lattice. These signals are extremely subtle, but our instruments continue to improve. Space telescopes and observatories are scanning the universe for exactly these patterns. So far, space-time appears smooth, but the search has not ended. Loop quantum gravity stands as a quiet counterpart to string theory. It does not require extra dimensions or new particles. Instead, it takes the geometry of space itself and applies quantum principles directly to it. Where strings are imagined to vibrate, loops are thought to weave. Both approaches in their own ways point to the same message. At the Planck scale, empty space does not exist. There is only structure quietly active beneath the surface of reality. This way of thinking reshapes how we imagine the universe. The cosmos is no longer a passive stage where matter simply moves around. It becomes a living network, dynamic and self-interacting. Matter curves space, and space guides matter in motion. Beneath both lies a hidden framework of loops and connections. As unusual as it sounds, this quantum geometry may be the key to bringing quantum mechanics and relativity together without contradiction. In this view, the universe is not built from particles sitting inside space, but from space itself becoming quantum. It has been suggested that space is not what it appears to be, but a web of relationships between quanta, giving rise to geometry only when viewed from a distance. This leads to an even deeper question. What if we look beneath the loops, beneath geometry itself, to a level where information becomes the most basic ingredient of reality? What if space-time is not only quantized but emergent? If distance is merely an approximation, what can we truly measure? What if the concept of distance itself is no longer fundamental? What if near and far, before and after, here and there, are only useful ideas that dissolve when examined too closely? This question marks a quiet boundary in modern physics. After centuries of observation and measurement from early telescopes to the James Webb Space Telescope, we are approaching a limit imposed not by technology but by the universe itself. This realization comes from two separate lines of reasoning that point to the same conclusion. One comes from gravity and the collapse of energy. The other comes from the quantum limits of measurement. From the relativistic side, Einstein's theory tells us that energy bends space-time. When too much energy is concentrated into a tiny region, space-time curves so sharply that light cannot escape. A horizon forms, and a black hole appears. This means that if we try to probe smaller and smaller distances, using higher and higher energies, we eventually reach a point where the experiment itself collapses into a gravitational trap. Beyond that threshold, nothing, not even information, can return. The act of measurement destroys the very thing we are trying to measure. The second line of reasoning comes from quantum mechanics. The uncertainty principle tells us that every measurement contains an unavoidable blur. The more precisely we know position, the less precisely we can know momentum. This is not a flaw in our tools, but a feature of the universe. When gravity is added to this picture, something unexpected happens. As the energy of the measuring photon increases, space-time curvature also increases. At first, higher energy sharpens position, but beyond a certain point the added curvature blurs it again. There is a balance where further precision becomes impossible. This idea is captured in the generalized uncertainty principle. According to this principle, below the Planck length, about 1.6 times 10 to the power of minus 35 meters, the concept of distance loses physical meaning. It is not that we lack a powerful enough microscope, it is that the universe itself no longer provides coordinates to define what is closer or farther apart. Two independent paths of thought, one rooted in gravity and the other in quantum theory, lead to the same boundary known as the Planck scale. At this boundary, Einstein's smooth picture of space-time and the probabilistic language of quantum mechanics are no longer separate descriptions. They collide, overlap, and demand a new way of speaking about the universe, a unified framework that treats both ideas as equally fundamental. The search for such a unification lies at the heart of modern theoretical physics. From this search, two major approaches have emerged. One is string theory, and the other is loop quantum gravity. String theory suggests that everything in the universe, from electrons to space-time itself, is made of tiny vibrating threads of energy. These strings are unimaginably small, roughly on the scale of the Planck length. Because of their finite size, they do not allow infinite sharpness. When energy is added, they stretch and vibrate instead of collapsing into a single point. In this picture, gravity arises naturally from the motion of these strings. Loop quantum gravity takes a different route. Instead of starting with strings, it begins with space itself. It treats the geometry of the universe as something quantized, built from discrete loops and nodes known as spin networks. In this view, areas and volumes are not smooth and continuous, but granular. Each represents a tiny unit of geometry, again, close to the Planck scale. Although these two theories differ greatly in approach, they point toward the same deep conclusion. Space and time are not fundamental ingredients of the universe. They emerge from deeper relationships beneath them. The smooth space-time we experience is like a mirage that appears when countless quantum interactions blend together. The universe at that depth is not clearly here or there. It becomes a web of interactions constantly shifting between possible states. This is difficult to imagine, yet it may be the birthplace of everything we observe. The laws that shaped the universe just after the Big Bang, the rapid expansion of space, the formation of matter, and the seeds of galaxies all trace back to this regime, where geometry itself was quantum in nature. Observatories have pushed our view ever closer to that beginning. Missions that mapped the cosmic background and modern space telescopes now allow us to see the universe as it was hundreds of millions of years after the Big Bang, when the first galaxies began to shine. Yet the true origin, the quantum instant when space-time itself came into being, remains hidden behind a natural wall of uncertainty. It has been said that we are a way for the cosmos to know itself, and yet the cosmos appears to have drawn a boundary around its own reflection. We can observe stars and galaxies. We can measure how space-time curves, but beyond a certain level of precision, nature refuses to reveal more. This is not a dead end, it is an invitation. If distance itself is only an approximation, then physics must find a language deeper than geometry, a description not based on where things are, but on how they are connected. In some ideas of quantum gravity, this is exactly what happens. Space emerges from entanglement, from the way quantum information is shared. Geometry is created by relationships. In that picture, distance is not a basic property of the universe. It is a result of interaction. Space exists because particles exchange information. Without interaction, there is no separation, no between. This is a radical but powerful idea. At the deepest level, reality may not be made of objects, but of relationships. The universe, then, is not simply a place. It is a process. These ideas have not yet been tested. They remain maps drawn at the edge of what we know, elegant and consistent, but waiting for evidence. This is where future observatories may play a role. By measuring gravitational waves with extreme accuracy, they may reveal how space-time behaves when pushed to its quantum limit. The stakes are immense. If subtle signs of quantum geometry can be detected, tiny distortions in waves traveling billions of light-years, we may finally glimpse a deeper order beneath relativity itself. Even if that moment lies far in the future, one truth already stands. The closer we look, the less we see. Not because the universe is hiding, but because the tools we use, space-time and measurement, begin to melt under their own precision. At the Planck scale, distance is not wrong, it is incomplete. A useful language that fails when the questions become too deep. What lies beyond may not be smaller or larger, but simply different. Space-time itself may be only an approximation, a shadow cast by a richer quantum foundation. And so after all our equations and observations, physics returns to wonder. To a universe where and when are not final truths, but patterns emerging from something deeper, more fundamental and still unnamed. When we reach the limit of measurement, science does not end. It changes, from measuring to understanding, from mapping the universe to sensing its structure through logic, mathematics and imagination. In that quiet realization, the cosmos does not shrink. It opens inward toward the fabric of what it means to exist.